let's have a look at the power supply. I've done a couple of updates. Let me give you a quick, let me give you a quick rundown of changes I've made. You guys have seen the raw power board. So this is a board that takes it from the transformer, purely does the rectification and then does some bulk capacitance and outputs it out the back. Main changes I've done here is just a bit of system design. I've made this board, I've added standoffs for the to stabilize the heatsink in the on the second board. This is still the Arduino standoffs, and I've got the power going up through these metal standoffs in the back, and I've simply moved them back a little bit, and the entire design now fits together throughout. You'll see that in some places the standoffs cut into the capacitors that I've drawn here, but these standoffs are vastly oversized. I would use the M2 ones so that they fit, well, the M2 ones for the Arduino, M3 for the standoffs and the power levels. So they should all fit happily and nicely. The main item I want to discuss is the power supply. So I think I've now finalized this circuit board, or this schematic at least, and I'll take you guys through this quickly. This is the entire thing. I want to specifically focus on let's say this section today, and I'll take you guys through quickly what my thinking was and what the calculations and things are, and how I see that actually working. On this piece of paper, I have just drawn out the sort of three little helper functions for us to work through. And what I want to do is I want to quickly reproduce the power supply circuit I have on the schematic, just so we can quickly discuss each section individually. Alright, so if we have a look, here's our, I'm going to draw my shunt, and let's call that shunt, right? And you'll see that I've got 10 0.1 ohm resistors, and these work out to be 0.01 ohm, right? And I'll go through why I've chosen such a low value specifically in a moment. And remember, the maximum volt or current through here is going to be 3 amps, right? So it'll be 0 to 3 amps coming through here, which will give us a maximum voltage drop over the shunt resistor of 30 millivolt, right? So what we do then, our shunt resistors sit there, and they go off to our load, and we take one from there, one from there, and what we need to do, we need to find the difference between these two levels, right? So we can read off this voltage drop across this, so we can work out the current therefore, because the resistance is going to be stable. So what we need is a differential amp. So I'm going to use op amps to do that, and the simple way to do that, a little bit crude, right, is if we have we draw first a an inverting op amp circuit, right, a voltage divider there. And we do the same on this side, where we have right, a voltage divider, and that goes down to ground. Right, so there's a little differential amp. Now the problem here is that because we have this feedback circuit, we are going to be drawing current from this guy, and we don't need that. So effectively we need a buffer in the middle. So if we add a buffer circuit, alright, and we do non-inverting and inverting, and let's get him going in there. And normally the buffer would just go a straight connection through there. It's a one-to-one amplification, and everybody's happy. However, what we need at this point, because remember this is the point there where we're going to do the current limit switching. So this we need to get to 3 volt, right? And I'll go through why, because I've chosen a 3 volt voltage reference. So we need to get this to 3 volt to be able to switch between 0 and 3 volts. So the maximum is 30 milliamp. So 0 to 30 milliamp there, millivolt. Sorry. So what I ended up doing was to put a voltage divider, or let's ground that, and RF, right, and he heads up there. Right. So I've chosen these values to be 18K and 2K. Right? So if we use our non-inverting amplifier calculations, we are going to get to RF over R1 plus 1, and that's our gain, right? And that works out to be 18K over 2K plus 1, which therefore equals to be 9 over 1 plus 1, so we get a nice even gain of 10, right? So that'll take our 30 millivolt up to 300 millivolt, and then our differential amp, I made a mistake, sorry, this should come through to there, right? So that's not a connection, right? And if we look at this now, I've chosen these values to be 18K and 180K, right? And you have to match those over here for our differential amp, 18K and 180K, right? And if we take our inverting amplifier calculation here, and we say AV is equal to minus RF over R1, and that is equal to 180 over 18, right? We get a nice even 10 over 1 gain, or equal to 10 as well. So it'll take our 300 millivolt and convert it to 3 volt at the end of the day. Right, so we have a perfect match for our voltage reference, and in the next stage of the power supply, we'll push that into a simple comparator. Right, let's say plus in there. This heads off to our Vref. Right, so sorry, this is Vref. This is actually not, well, it's based on our Vref, but it is our current limit, C limit or set limit, I set. Let's call it I set. Right, current set, which will push a voltage in here, which I'll go through the circuit in a moment, which will push a voltage in here from 0 to 3 volt, and as soon as this voltage on our inverting line is lower than that, it'll turn this thing on, which will effectively then go through and turn on the transistors, which will pull the voltage set line low completely, right? So this is our current set equation so far. So effectively, if we look at this section here, is effectively a buffer, but it's a 10 times gain buffer, and this section here is a differential amp, and here they go into our comparator and turn our well, we've got a current limit LED or setting in there, which will turn off, and it'll also pull this line down to bring the set voltage down. Okay, I've redrawn the circuit just to clean it up a bit, because it was very neat. Not that I think this is much neater. But let's quickly look at the rest of the circuit, right? So we went through the first couple of sections where we had our non-inverting buffer, which we added a 10 times amplification to take it from 0.03 volt to 0.3 volt. We had a differential amp setup here, and again we pushed through a 10 times amplification with matched pairs there and there and there and there, 10 times to give us our 3 volt, which is equal to our 3 volt voltage reference. So our voltage reference is equal to 3.0 volt, right? So that matches up nicely with that. Then what the next part of the circuit is effectively a comparator. What the comparator does, it compares these two values, and if my I set voltage, because remember this is set via a I squared C I to D D to A converter, and so we set the current that is allowed to flow through the circuit by setting this voltage on this pin, and if this voltage is ever lower than the voltage detected over here, due to the high gain of our op amp, this circuit turns high, right? What happens at that stage? If this circuit turns high, it sets our current limit too high. Obviously this current can flow through this transistor then, and similarly it does the same thing for this transistor, which then pulls our control voltage that goes to our linear voltage regulator, the 3080s. It pulls that low, which effectively turns off our voltage regulator. So let's see how that builds into the voltage control section. So here again, I have a single 3 volt VREF, and I reference that voltage throughout the system. And again, there's another I squared C digital to analog converter, yeah, which we'll go through in a bit. And yeah, in this case we have a non-inverting amp going. And what we've got here is, if we look at these, we've got a 1K and two 18K resistors. Why 18K? The reason for that obviously is because we've specified 18Ks in a couple of other places, so let's just reuse those, buy them in bulk, it's much better. So what do we get if we get two 18K resistors in parallel? We get 9K out at the other end, right? So if we look at our gain equation here, what was it again? We have it here. So our gain equation for a non-inverting amp is RF over R1 plus 1. RF in this case is 9K over our 1K R1 figure, and we plus 1, and that obviously gives us our gain, right? And we again have 9 plus 1, which is equal a nice round 10 times amplification. So if we apply 0 to 3 volt on this end, we are going to end up over here with 0 to 30 volt, which we then send off to our LT3080 voltage regs, with the limitation of, if ever this current is higher than the set current, right, it pulls this line low, which brings this line low, which turns our voltage regulator off. Okay, let's go back to our circuit diagram. Let's quickly go through the rest of the circuit. So we've discussed, so for this entire section, there's our shunt resistor, our set of shunt resistors. We've discussed our non-inverting buffer. We've discussed our differential amp. We've discussed our comparator, and we've discussed our V set or voltage set non-inverting op-amp circuit. These go to a three of the LT3080s, right? The reason for that is they are nicely parallelable, but each of them can only deliver 1.1 amp. So 3 of them in parallel, we can set them to, so effectively they should be able to provide 3.3 amps. So we have 300 milliamps spare, above full capacity. Then what are we doing with this LM334? This is a constant current source, and the reason we do that is to make sure that we are drawing the minimum current required for this thing not to drop out. So for it to go down right down to 0 volts, you read the data sheet, it needs to be supplying a minimum of 10 microamp or 10 milliamp, sorry, and this is what this circuit does. So this circuit constantly draws 10 milliamp. We've got some protection diodes, and that's the bulk of it. If we come back to this section now, so here's our shunt resistor. So here I've got a spreadsheet just quickly to look at. I just played around with some figures here. And the idea here is to put 0.1 ohm resistors, but 10 of them. Why 10? Because resistors in parallel, you obviously get the formula of 1 over that, and that all equates to 1 over the sum of those. So I've added those formulas in here, and it comes out to be 0.01 ohm, which if you push the maximum of 3 amp through this shunt resistor, it'll dissipate a maximum. It'll have a maximum of 30 milliamp voltage or volt drop across that resistor, which then also equates to 0.09 watts of power being dissipated, which means if we have these 10 resistors and we use standard quarter watt resistors, the total wattage we can dissipate through this network is 2.5 watt, right, which is way higher than our 90 milliwatt required. So we don't need these enormous shunt resistors that have to dissipate loads of heat, because these guys aren't going to heat up much. The reason we specified a maximum of 0.03 volt across our shunt resistors is because of the chip we selected for our voltage monitor. So the INA226, if we have a look at that data sheet, we can see that if we scroll down a little bit, we'll see that the maximum shunt voltage input range is between minus 81.9175 and 81.92 millivolt. So we cannot just add a 1 volt drop across our shunt resistor. The maximum is 80. So 30 millivolt is a bit lower, and given that this has a 16-bit signed analog to digital converter inside here, we should have plenty of resolution to get some decent measurements out of this. The other reason I like this chip is because it has the V-bus monitor. The V-bus monitor allows us to, as you see here, there's our V-bus monitor, and I can measure right out to the output voltage to confirm that is what is being sent out. A secondary measurement will be taken from our sense pad. So if we bridge these two connections, here's a voltage divider which brings our 30 volt down to 3 volt. Again, that's just a 10 times divider. Let's have a quick look. We have 18K, two 18Ks in parallel with a 1K, and that gives us a nice 10 times divider. So we can send this off to our Arduino, which is also making use of the 3-volt voltage reference. So everything is nicely synchronized like that. Okay, so yeah, as I said, there's our voltage, our V set, our current set circuit. So it's an I2C device. It takes an input of a voltage reference, and we get the analog voltage coming out here, 0 to 3 volt. Similar with our voltage set, our V set section, exactly the same thing. Yeah, you can see the 3 volt voltage reference into the same chip. We get our 0 to 3 volt out here, which is multiplied by 10 to get our voltage current set. Right, and that's effectively the full circuit, the power supply control circuit for our power supply. What I've done here is this is simply an off-board connection to connect to the other board. So we take all the important pins out here, feed it through to the control, the microcontroller board. The only other things you can see here is our 3.3 and 5 volt static voltage references here. I've added the same current and power control circuitry or voltage monitor circuits to these, just to monitor exactly how much current these two circuits are pushing. I am planning to use the V803-1500 chips here. They are a drop-in replacement for the 7805 type circuits, but they are switch mode regulators, so they should be they're much more efficient. You get much higher current out of them, 1.5 amp each of these, so we should be more than enough to have a decent charger. So these two are both coming out to a port on the front. However, the 5 volt I also want to push out to a simple USB charge socket, so you can plug in a USB device in there and power that device as well, while then in circuit monitoring the voltage and the current being supplied to that. And that's it. Okay, so the only other thing I wanted to quickly show you guys, I've updated these off-board connectors. So there's our Arduino connections. There's our, you saw that this is a heatsink I've selected as well, and just a slightly more rigid connection through to the case or to the mounting points. These are metal standoffs which connect our raw power connection up to our control board, which in turn there's that off-board connector we're talking about that comes through to the microcontroller motherboard. The top board gives us access to our LCD, this LCD out, mode and switch and LED outputs over there, current limit LEDs, our voltage and current set optoencoders. In the back there we have our WSLAN connection, which I'll go through in the next video, some fan and temperature pulse width modulation control there. In the back we have our two switch mode regulators, which currently drawn as standard TO220s, but they just becomes little square or rectangular boxes, but pretty much the same space being used. And there's our three paralleled LT3080s mounted on a heatsink in the back there. The idea obviously being that this leaves space for our transformer to sit under. Nice compact control. Transformer is tapped into these, pushed through to this board over there. These connectors over there that you can see are the ones that go off to the front panel. So that'll be our sense connector, 0 to 30 volt, ground, 3.3 volt and 5 volt, and our USB connector. There's our USB circuit that'll go off to the USB charge circuit, which will go off to the front panel USB as well. The idea obviously is that from our Arduino we'll also have a USB cable running out to the back of the case with a system control and monitor and connection USB port in the back there, together with our WSLAN connector in the back. So yeah, that should all be quite good. Obviously on the back of the case we'll have our pulse width modulated fan blowing air straight onto our heatsink as required, because it's pulse width modulated. And yeah, so next time we'll go through our top circuit and start talking about a little bit of designing of the logic, etc. In more detail. Right, if you guys like that video, keep the comments coming. Tell me if I've done something completely crazy. If you have any better suggestions or thoughts, please let me know. But if you like the video, thumbs up, tell your friends, tell your family. Let me know. Thanks guys, cheers.